Hey there, everybody! Welcome back. We've got our new theme song now, so we're really official in this live stream business here. For those of you who are coming back, I actually have to remind myself because I've been working on other things all morning long, but I've got the notebook up that we were working with last week, and what we had done so far, just looking at this, I believe what we had managed to do so far is write some features to convert that input string that we're getting out of Zeek. You might recall that we had this broker script over here that's able to interact and receive that stream data right into Python here. And this feature here, this method here, was going to convert that out to bits for us. And then we push that out into a CSV file, and we've read that back in, and we currently have our data sitting in memory. And we've even done a couple of other manipulations to it. In particular, we know how many different labels there are. We've pulled our data in and shuffled it because I was pointing out that while it is true that it's going to shuffle the data before it does the training, if I'm going to set aside some data for doing validation, for instance, I should really probably shuffle that data ahead of time, either for validation or maybe for some test data. And so we're going to do that. So I shuffled it up. And then I peeled apart the data and the labels. And I believe where we left off was, we know what unique labels we have, but what I need to do right now is I need to convert these within that Y labels array. So if we have a look at it right now, that Y labels array is got, I can't remember how many rows it is, 596,000 rows of text. I need to convert those over into numbers. And not just any number. What I'd like to do is map them over to the index locations for where they are in this unique Y labels array. And in fact, I think I'd like to capture that. I'll call it unique labels because I'm going to need to map between the two. That's going to be good for our output. Let's make sure that works. I am a little overly cautious. I like to make sure things work just fine. So now that I have that there, how can I convert that into something I can use for a mapping? Because I can easily give that a number. Let's look at unique labels sub 5. That's easy enough. But I need to go the other way. I need to take HBBTV discovery and come back with a 5. Well, it makes a lot of sense to me to take that and turn it into a dictionary. And I think what I had said last week is there's this thing called label encoder that's from sklearn that kind of automates this for us. But in thinking about it over the last couple of days, I thought, let me just show you how you do that so that you don't have to bail out and go use a library function. I mean, library functions are great, but you should know what they're doing. So let's just build this. Let's create a dictionary. So I'll call it label dictionary. And we're going to use a dictionary comprehension to do this. Now, much like a list comprehension, it lets us iterate over things. But a dictionary comprehension is supposed to be iterating over keys and values from a dictionary. That can make you feel like I can't use this because I don't yet have a dictionary, but that's not true. It turns out that the dictionary comprehension is a little bit more flexible than that. And as long as I am giving it a tuple, it will work just fine. The tuple that I'm going to get, let me actually show you where it's going to come from. I'm going to be using an index value and the protocol name in the enumeration, or to enumerate the enumeration of unique labels. So the only thing I need to add to that is what's happening in the dictionary. Well, what I have right now is an array, and I can query the array by using the index number. So what I'm trying to turn this into is a dictionary where I can give it the protocol name, and it gives me back the index number. So let's see how that goes. So I'll run that code. That seemed okay. Let's just see what our dictionary looks like. And we can see now that I have numbers assigned, index numbers assigned for every one of the things showing up in this array. Now, you may be looking up here and saying, well, that's not the same order. That's okay. This was actually something else I was printing out. I'm not sure. Oh, I was looking at the first 10 values. So that's not actually the unique list. But let's put side by side the unique labels array. And I find that the first thing in there is the boot service discovery protocol. And that is, in fact, the first thing in my dictionary. The last thing is TLS response, and that is the last thing in my dictionary. I'm now ready to go ahead and encode those labels. To do that encoding, I'm going to use a list comprehension to do it because I currently have that data sitting in Y. What is that sitting in? It's sitting in Y labels. Looks like that. And I think what I'm going to do is change it into Y. I don't know what we want to call this. How about Y encoded is going to be the the list comprehension, where we're going to take the label dictionary value, label dictionary, my fingers will type, for the protocol or protocol in Y labels. Because Y labels, remember, has this list of strings. So hopefully that's going to do it for us. And if I look at Y encoded, I now have a list of dictionary names or index numbers that are coming out of that unique labels. Excellent. They're encoded as numbers now, but we have another small issue. Let me just bypass that issue for right now. We'll come back and fix it when we get to it. Let me look at my data because I actually don't remember what that looks like. My data, well, my data is close. It is currently a NumPy array of strings, or really they have characters in them. And I kind of need to turn that into uh, numbers. Now it ended up this way because I pushed it into that CSV file and then pulled it back out. I did that because I needed the labels on them. And NumPy arrays need to be homogeneous. So that means within a row, my columns need to be all the same type. I couldn't have a string protocol and a bunch of numbers with it. It would be very upset about that. Now I've just got a list of strings, and those strings all contain numbers. So I'm just going to translate that. I'm going to say take that, and let's interpret that as type np dot, and I'm going to make them float 32. It's just an arbitrary choice. I could probably make them, actually, I feel really confident that I could make them integers with no real detriment, but I'm going to go with making them float 32. And that's just from my experience and knowing what's going to happen inside of the network. I feel like making them floating point numbers is probably just going to save us maybe a little processing because everything is going to be a floating point value. Having done that, I can see, in fact, they have been changed to floating point values. So I'm pretty sure that the only thing left to do then is to maybe set aside a test data set. Let's do that. So I'm going to say that my X train is going to have X data. It's going to take, let's see, how many rows do we want here? How about all but the last 10,000 rows? And I'll say that Y train, I'll do the same thing there, is Y encoded. That should be the last 10,000, or the first 1,000, sorry, all but the last 1,000 rows. Let's set X test, so the data that we'll use for evaluation later is X data. 1,000 rows back to the end, so the last 1,000 rows, and we'll do the same thing for Y train. Y encoded, whoops, that should be Y test, sorry about that. Y test going to be from 1,000 back until the end. If that goes well, let's just have a look at some of our shapes here. So that is that many rows in length. Let's look at X test dot shape. And that one's 1,000 in length. So, okay, so those lengths all look okay. It looks to me like we have properly pulled that data over. And that should mean we're ready to start building the network. So let's do that. And when we do it, we're going to run into that problem that we have with our Y data right now, with our labels. Right now, our labels are integers, and there's something about that that's not quite going to work. To create my model, I'm going to begin by just creating a model, and I'm going to use the standard API for this rather than using the functional API. Let's see, rand show, my fingers will type. It's kind of cold in my office today, so my fingers are not happy. And I'm going to add a couple of layers to this. So let's add to this layer model.add layers dot, and I'm going to start with a dense layer. A dense layer, or a fully connected net layer in machine learning means that all of the neurons in this layer will be connected to all of the neurons in the next layer on. It doesn't connect to every other layer, it just connects to the very next layer. And in fact, we're going to build a pretty simple model. We're not going to use any convolutional networks or anything. It's just going to be a straight, dense network. And it turns out we can do pretty well just using these dense layers. So arbitrarily, I'm going to say, let's use 64 neurons for this. There's no special reason for this. In fact, I've got some genetic search algorithm code that I've got that I usually take a modeled network and run through to do hyperparameter tuning to figure out how many layers should we have, what kind of layers, what activation should they have, all those kinds of things. And I'm not going to worry about what those numbers come out to, but I know that using something like 64 here is going to work out to be just fine. There's no formula for this. This is just intuition based on experience. 64 neurons should be okay. There is no special reason that this is a power of 2. There are some myths floating around about that. Absolutely not. It's just arbitrary. We tend to use things that are powers of 2 with computers. And in fact, I read a really interesting paper about this. Someone was asking, so why don't you see things like 71 or 69 when you look at published models? And the answer was fascinating to me. The response was, because if you did that, a reviewer reading your paper would say, why is it 71? Now, if you used 32, 64, 128, 512, 256, no one would raise an eyebrow because we arbitrarily just pull those numbers out of the air all the time. But if you use something like 71, the reviewer now wants to know, why is that? Why does it have to be 71? Is maybe your model not general enough that you have to be so specific? So it's kind of curious that if you were to tune it, you end up getting more questions than if you just pick random values. In any event, we're going to use 64 neurons here. Let me set my activation to be rectified linear unit. And because this is also the input layer, or in reality, this kind of conceals something from you when you do this. If you built this as a functional model, you would actually build an input layer and then your first dense layer. In the API, it's actually adding another layer there for the input and then the dense layer. So it turns out this first dense layer really is a hidden layer, and there's an input layer there that you don't really see as you're writing it, but it's magically just adding it in. To add that in, let's use the shape of X train, and in particular, we want the first value in that shape, which is going to be how many columns there are, so how many features there are. So that ought to be the shape of that data. Whoops. X train shape, that all looks fine. And then let's see what else I need to, oh, actually, I think I want, because this really does expect a tuple in there. So let me just put a comment in there. Let me add in another layer here. This will be layers.dense. And again, arbitrarily, I'm going to move this down to 32 with an activation equal to relu. And that's all I need in there. Let's actually make one more of these. How about we, I don't know, make it a little bit autoencoder-ish. So we'll scoot down to smaller layers, and then we'll bump back up to a larger layer before we try to produce some output. All right. So we now have the network more or less defined. The only thing that's missing is the output layer. So let's define the output layer. Model.add layers.dense. This is also a dense layer because it's going to have neurons that are connected to everything before it. And I need to say how many neurons it needs. Well, what we're doing is a categorical problem. This isn't a regression. A regression is going to create a continuous function. It's going to tell you a continuous value. Right now, our labels are numbers ranging from 0 to 12 or something like that. They're really not continuous. I mean, they're discrete numbers. I could actually build this with one neuron and have it attempt to do a regression, attempt to fit to a regression to find which number matches. But that's not a great way to go, because It might be that the data I'm looking at has features that are similar to many of the different categories, but which one does it match most strongly? So what I really want to do is have a look at the length of, now what's my name of my labels here, unique labels. So let's make it the length of unique labels. I want to have that many neurons, one neuron for each category. That's great, but when I do my fitting, I need to give it the X training data that is the correct shape. So here's the shape. That's going to be the right shape. And my labels must also be the right shape. And they are not currently the right shape. They're not the right shape because my labels are a one integer value. So I need to convert them into something that is however long that is, that many fields, that many features or categories, not features, excuse me. How can I do that? Well, I'm going to come back up here in this cell here. I'm going to add in a little bit more code. What I'm going to do is just take a super easy way to solve this problem. What if I take each one of those numbers, each one of those labels, and I were to one hot encode it into a field of length unique labels? That would solve my problem because now all of my labels would be the right size. Here's how I can do that. Let me take my Y train data. I'm going to store that into Y train one hot. And the way I'm going to apply that is using a wonderful utility function that's available in Keras. So in Keras utils, we've got two categorical, which that's a pretty convenient name. Even I can remember that name. Let's do that for our training data and for our test data as well. PF Keras utils to categorical y test. All right. Whoops. Should probably one hot. Don't know what my fingers are doing there. All right. So I now have that data encoded as one hot encoded data. Let's just see what that looks like. Let's look at the very first element. And you can see I now have a field that is however many unique labels I have long, and only one of those is turned on. It is now the right shape. Well, then I can compile this model, compile this, something TensorFlow can use. I'm going to use the optimizer of RMS prop. Not for any particular reason. I've done this before. That optimizer tends to work pretty well. There's a bunch of different ones you can choose. One of the things I usually tune in my hyperparameters is which different optimizer tends to work best for this problem. And I need to specify a loss function. That is going to be categorical cross entropy. Very simple reason why, because there's multiple possible outputs, and I'm trying to measure the loss across all of those, a categorical problem. So categorical cross entropy is the right way to go. And let's set our metrics to be accuracy, just because I always track the accuracy. Right, whoops, I've got something a little bit wrong here. What am I not happy about? Oh, optimizer. Whoops, where's my, there we go, optimizer. Nope, still something wrong here. This is up here, model.add 64. So it's one of these. And it's got to be this one here. So what's it not happy with there? Input shape. Oh, input shape equals, there we go. Has to be an equal sign. Wonderful. Now that I've got all that in there, oh, well, okay. We were looking good. There's something it's still not happy about. Int is not iterable. What is it looking at there? My input shape. Shape. Let's just pull the shape out. So I'm going to do that up here. X train.shape instead of fighting with it. Okay, so it's 128. 128. And oh, got something else wrong here. I might have a parenthesis problem. Let's see what's not happy with. So this is in the 32. All right, that looks like the right number there. Oh, I've got too many parentheses here. Yes, I Or do I? No, no, those are the right number. Oh, why is it not happy here? So my input shape is 128, and then I'm having a problem on this 32 layer. Model.add invalid syntax. It's not jumping out at me what's wrong here. I'm going to just try commenting that out just to see what happens. Yep, and now it's not happy with the next one. So the problem is definitely on this line here. Is it not happy with me sending that with a comma? Is that possible? Oh, no. That one is missing a parenthesis. That is totally the problem. Okay. I was right. It was a parenthesis problem. I was just in the wrong place. All right, we've got some other issue here. D-type to the constructor. Down here it tells me unknown loss function, categorical cross-tripy. Okay. I don't know where you guys are today in the comments. You should be helping me out here. Cross-tripy is definitely not the same as cross-entropy. Finally, so the model now compiles. With that done then, just clear out that cell. Let's try to fit this. So training history equals model.fit. And I'm going to pass it the xtrain. I think that's the right name of it. Yep, xtrain. And ytrain one hot, which is the proper shape. I'm going to set a validation split of 0.1, so 10% validation. I'm going to do epochs 5, and let's do a batch size of 32. All right, I think that ought to do it. While that's running, the idea about the batch size, I know people kind of struggle with that, and I hear different explanations for what's happening there or how you pick it. Usually, you want a batch size that's somewhere between, say, 20 and 40 or 30 and 40. But why? What does it do? There have been cases where I have used a batch size different than that, and it's worked out super well. However, more often than not, you want a number in that range, because what this number is defining is how frequently will it go back and update the model, update the weights and the biases. That's really what it's tracking. Now, while this is running, I'm watching this and I can see these numbers, and wow, this looks really concerning. This is telling me, looking at the validation loss and looking at the accuracy, my goodness, this is exceptionally low. It's making me think I've got something that has gone wrongly somewhere in my model or somewhere in how I've processed the data. Now, I'll tell you, I'm not going to try to troubleshoot that one. Instead, I'm going to be a little bit like Julia Child. And this is just totally convenient. This is absolutely coincidental because I have, sitting over here, let me stop my screen share for just a moment. Let's add in a different screen here. Because it turns out that earlier today, let's see which one I'm looking at. It's this one here. I was actually building this out as an example of something that is being used in a class. So I'm pretty sure I'm sharing with you now a different model. And you'll see that this looks quite similar. It's not exactly the same, but it's very similar. I'm instead here using TensorBoard to measure what's coming back on it. But you can see that otherwise the model is really the same design or very close. And in fact, it's solving the same problem. It's got a little more text here. This is actually, so this is a little excerpt out of the 595 class explaining how we're going about building this kind of a network, what we're working on right now. So in any event, if I come down here, you can see that in the end, my model, when I train it properly and don't make whatever mistake I've made in the other one, likely with my data, that I end up here after just a handful. Let's see here. I mean, I'm at 98% in the very first epoch. I think I've got the TensorBoard data for this too. Yeah. So at the end of the training, my validation accuracy is 99.8%. That is pretty good. And what I can do with that then, with that model, is I can now make predictions against that data. Making the predictions turns out to be a really simple thing to do. Now, I've got some other code in here, and I'm going to stick with this one because I know this model is working. I've got some example data. Let's see here. What do I have happening in here? So this is not exactly the right stuff here. So I'm going to just chop this out because that's leftover stuff I haven't edited yet. Let's take my test data. Let me see how I've named that over here. It's named X test. Let's pass or do a model.predict x test. So that's going to be all of my test data, predictions. Awesome. And so in here, well, let me just add a cell for that. So that's actually, it's done. It's done the predictions. If I look at one of these, the predictions don't look very intelligible. But if I push that into something like argmax, it now tells me which of those neurons is most lit up. And I can now use that with unique labels, say, oh, that first packet, it is predicting that it is an SSDP packet. So what do I do with that? How do I know if that test data works? Well, I could use the evaluate function that's built in, but let me show you it a slightly different way. Over here, I've got some test data, some DNS requests in this case. This DNS content is, let's not do it this way. This DNS content is data that has not been used for training my network. So what if I were to do a prediction on this data? How do I want to do this? So let's do model.predict. I'm going to have to futz with this a little bit. And it's expecting an array. So I'm going to give it an array. And the array it's going to get is the current content. And what I want to do is get the argmax of that. And then that whole thing, I want to take a look at what the label is. Labels. All right, hopefully, see how we do there. Nope, not happy about something. It's probably how I'm passing in my array. Input lower. Oh, that's interesting. So what shape is coming in on that? Oh, it's because I need to convert these over to features. My features will be, and I forgot how I've named it here. Close your eyes for a moment if you get seasick, because I am going to do some fast scrolling. Let's just scroll way up here, because I wrote a function way up here called bytes to bits. Is that what I want? No, I don't think that's it. Content to features. So content to features is what I'm looking for. So let's try to use content to features against that. I'm back where I was. Here we go. All right, you guys can open your eyes again. Content to features against my content. Let's see if that's happier. No, that's still not entirely happy. Well, that's just how live demos go sometimes. Oh, that's interesting. So it should be turning that into features, but it isn't. Maybe that function doesn't do what I think it does. I feel like I'm in the Princess Bride here. So content to features, content. Let's see what that does. Nope, that gives me an array of 128 bits. What is this not happy about? I don't see another obvious problem there. And look at this one more time. Input layer sequential incompatible. Show value 128, receive 32. Yeah, well, I think I've got 128 there. Let's just see what the shape of that is. Whoops. See what the shape of that is. It is 128. All right, it's just not happy. I'm not going to fight with it more. Instead, I'm going to go even one step further. We're going to cheat even more. Let me share a different screen. And what I have here is a machine that's actually running live. So let me modify my share here and send you out just one last thing to wrap things up here. This is a terminal window somewhere. Let's see which one it is. It could be this one. I think this is the right one. It looks like it is. I'll just wait for that to show up for you guys. All right. And what I have running in here is I have a script that is making use of really the stuff we were talking about, the stuff we've done in this demonstration over 2 episodes, but it's all broken out into functions because clearly I'm going to need to do this more than one time. And in fact, it's also glued to that broker thing that I started with in the very first one last week, where I was pulling the data straight out of Zeek. Further down, you can see here that it's loading in a trained TensorFlow model, which is actually where we were heading until everything went off the rails with really bad training results. With that model loaded, then, all this is doing is looping through, looking at the results that are coming back out of my Zeek. And that data is all being spooled in real time into this class log file. Now, I currently have it set that it's showing me everything, whether it knows it or not. And here's the really important intuition, the really important takeaway, how you can use this to do real-time anomaly detection. Notice that, for instance, this stuff, this is port 53 UDP. The chances that that is DNS is super high. And in fact, when it does its analysis, it says, yes, I believe that is UDP DNS. Same thing here. This one here, 99.96%, that is NTP data. Here's the thing. When we train a network in this way, it turns out that if it knows what it is really sure what it is. In other words, that neuron will be really lit up, usually above 95% or so. But if I give it a protocol it has never seen before, now, if I look at maybe the beginning of this class log, these are some older ones. See if I can find something that still has, well, how about this? Tail 1000 class log. I don't want to look at too much old data here. All right. So down here, we have something on port 49317 to port 48161. I have no clue what that is. Now, it has been categorized as NTP because when I do a supervised categorical training, it must come up with one of the categories. There is no category for unknown. But notice the confidence. We are well under that 95% mark. And in fact, I can see that's true for this data here and here and here. And the lower it is, the more likely it has no idea what this stuff is. Which means that in my Python script, I could use that as a threshold. And I can say if you are less than 95% confident, then let's just say you don't know what it is. Let's call that an anomaly. Because now I can put that in front of a human. I can send that out to the sim, let it know there's something weird happening. The human can look at that and make some decision. Now, I did have someone write to me in between since the last episode, and what they wanted to know was, listen, do you do anything with incremental learning? And it's a good question, and this seems like a place where you might do that. And I want to explain the answer that I sent back. Because in incremental learning, what we will usually do is set it up so that it is continually improving the model. We do not do it in that way. Instead, what we're effectively doing is transfer learning, which means we take an existing model and then we do some additional training with it, or at least use it as the basis for some additional training. So we do that, where whenever we see some new protocol, we add in additional neurons for the output and do transfer learning. Or if we find that it is miscategorizing something, it should know what this is and it's gotten it wrong, we will again, in that case, be doing incremental learning, really transfer learning, but we're not doing it continually, which is why I wouldn't just call it incremental learning. Still, there's lots and lots of ways to do this. Now, I know this was a really fast run through over 2 sessions, and it's hard to believe it's already been more than an hour total. We're going to stop this one here. And if you've got questions, you're welcome to reach out to me, and you can get in contact with me through SANS. Some of you have gotten me over LinkedIn. That's totally fine. We are, or at least I am, thinking about whether or not some kind of a regular live stream makes some sense. So if I could ask you, if you feel like there could be some value in that, could you let us know? And even if you have some suggestions of what those topics would be, maybe it would be about machine learning and AI. Maybe it'd be InfoSec in general, or blue team kinds of things, or red team stuff. I just don't know. Let us know, because I'm not committing to it, but we sure are examining whether or not that just makes sense. I thank you so much for your attention. If you've got any questions or anything, feel free. You could put them in the chat as we're going, or feel free to reach out to me at the end. Thanks so much for your attention. I hope you have a beautiful afternoon.